Hi guys, welcome back to my YouTube channel. If this is your first time, please don't forget to like, share, and subscribe. And when you subscribe, please turn on the notification bell so that you'll be getting updates of new videos. We're still looking at functions. I want us to cover everything on functions so that you can have good knowledge of function. You'll be able to use it to solve any problem that comes from functions. So for today, we want to look at types of functions. Please, if you want to understand some basic things about functions, like meaning of functions and how to represent functions, please watch the previous video. But today we want to look at types of functions. But before we look at types of functions, I want us to look at this particular thing, which is it that all relations are functions? Because remember, if you look at what we said the function is, we say the function is a relation or a rule which assigns one element from an input set to another element in the output set. A unique element, by the way. It must be a unique element. Now the question is, are all relations functions? And please don't forget, what did I say is a relation? I say what should come to the back of your mind when we talk about relation is what? Relation or rule is what? Equations. Equations should come to your mind. So now the question is, are all relations functions? The answer is what? No. Not all relations are functions. There are some relations that are not functions. Are we together? There are some relations that are not functions. For example, a relation like this, f of x, can you see this? Let me use black mark. A function f of x equals to square root of x. This particular relation is not a function. This is not a function. Are we together? This relation here is not a function. But if you have a linear equation, a linear equation is a function. For example, I have f of x equals to 3x plus 2. This is a function. A quadratic equation is also a function. F of x equals to, let's say, 3x plus 2x minus 4. This is a function. A cubic relation or a cubic equation is also a function. F of x equals to 3x squared plus 2x minus 4, 3x cubic, 3x cubed plus 2x squared minus 4x minus 6. This is also a function. It's also interesting to know that if you see a function like this, we call this modulus function. Modulus or absolute value. So what you have is absolute value of 3x plus 2. Is this a function? This is also a function. So this is a function, this is a function, this is a function, this is a function, but this is not a function. Now I want to show you another way of knowing what is a function and what is not a function, and that is we are going to be using an arrow diagram and graph to show. So there are some conditions you have to look at before you determine if a relation is a function or not. There are some conditions you have to look at. So now, using mapping on arrow diagram, please let's look up. Look at I have here x, I have here y. Is this relation a function? Let's check to see. Now, given a relation, let's say I have here a, b, c, d. And here I have p, q, r, s, t. And you now have something of this nature. This comes here. This goes here. This comes here. This goes here. And this goes here. Now looking at this particular mapping diagram, does this mapping diagram represent a function? That's the question we need to ask. Does that mapping diagram there represent a function? Does this mapping diagram here represent a function? The answer is what? No, it doesn't represent a function. Why? Now, that is one of the conditions you need to look at when you are looking at a relation to be a function. And what is the condition? That the condition says that any element in your domain, which is the input element, must have only one element in your range. So it means that if I put in an element, one element should give me one output. So one element cannot give me two outputs. If one element gives me two outputs, then that is not a function. So in this case now, this particular mapping diagram does not represent a function. The relation here is not a function because the element B in the domain has what? Two images. So, and that's the same thing that happens here. This particular function, f of x equals to square root of x, if you take an input element like 1, if you take 1, if x is equals to 1, your f of x will be equal to square root of 1, and square root of 1 is what? Plus or minus 1. Square root of 1 is plus or minus, that's plus 1 or minus 1. That's what it means. So square root of 1 is plus or minus 1. Now some people might say how? How? We'll get to understand that by the time we'll be looking at quadratic functions. See, by the time we're looking at quadratic functions, you get to understand quadratic functions, quadratic expressions, quadratic equations. You get to understand why square root of 1 is plus or minus 1. So that is why for looking at this, one input gives you two outputs. You input 1, you get plus 1, and you get minus 1 as your output. So such a relation like that is not a function. So this is not a function because the element B has two images. Now another one that is not a function is this. Let's say I have P here and I have Q here. Now P is my domain, Q is my range, supposedly. Then I have X, Y, Z. I have 0, minus 4. Then this guy comes here, this guy comes here. Now looking at this relation, is this a function? The answer is what? No, this is not a function. Now the question is, why is it not a function? Now for this mapping diagram to represent a function, all the elements in your domain must be mapped. All the elements in the domain must be mapped. So if you look at this, the element Y does not have any image. It's not mapped. So since the element Y does not have any image in your range, that means this particular relation here is not a function. Just like this one. This one is not a function, this is not a function. And please take note, why did we say this is not a function? Number one, if you look at this, the element B has two images. So that's why this relation here, F, is not a function. Now here, why is G not a function? G is not a function because in the domain, there is an element in the domain that does not have an image. So since an element here does not have an image, this cannot be a function. So these are the two conditions you have to look out for. If a function is given to you in this form, using mapping or arrow diagram, if it's given to you in this form and they are asking you to check if this is a function or not, these are the two things you look at. Does the function have two images, or does an element in the domain have two images? If it has, then it's not a function. Are all the elements mapped, or are all of the elements assigned? If there is an element that is not assigned, that means it's not a function. So those are the two of them. Now to look at graphically, we can also check if a relation is a function graphically. And for me to do that, I want to draw about, let's say, 4 different graphs that you see. x-axis, y-axis. This is the line here represents my function. So this line is y equals to f of x. A line that is a straight line, any graph that is a straight line is called a linear graph. Linear graph. So it means that my f of x here is linear. I'll explain all of this as we proceed. So a linear graph is a graph in which you have a straight line like this. Now the next graph is for this one, you see it is curved. It's not straight line like this. When a graph is curved like this, how does it look like? U-shape. U-shape and N-shape graphs are called what? Parabola. And what is this kind of graph? It is a quadratic graph. Quadratic graph. So our f of x is quadratic here. Now, for this one, x, y, if I have a graph like this, y equals to f of x, this kind of graph that looks like this, it has u, it has n, and it has u. This kind of graph is cubic graph. So I will say f of x here is what? Cubic. Then we have modulus graph. Let me try and put that. Modulus function x and y. Graph of a modulus function looks like this. So this is y equals to f of x, where f of x is a modulus function. Y equals to absolute value of f of x. Let me just use this. So I will say this is a modulus function. Y equals to absolute value of f of x. Then look at this other one. I'm trying to get my curves to look beautiful, because actually math is very beautiful. It's one of the most beautiful subjects. So this is y equals to f of x, where f of x is equals to square root of x. So you have this. Now look at, we have 5 different graphs. This is a linear graph. This is a quadratic graph. This is a cubic graph. This is a modulus function, graph of a modulus function, and this is graph of f of square root of x. Now the question is, how do we know that this is a function? This is a function. This is a function. This is a function. This is a function. Now to check if a graph is a function, we do what we call vertical line test. That's the condition we use to check if a graph is a function. Vertical line test. What do we mean by that? Look at this ruler I have here. This ruler, if I place it straight like this, it makes up a vertical line, right? Now what we do is, if I have this ruler as a vertical line, not horizontal, it must be vertical. As this ruler is like this, from here I move it from the left hand side to the right hand side, or from the right hand side to the left hand side. Now as I'm moving it on my graph, the vertical line test says that the line on the graph, or the curve, must touch this particular vertical line. So this ruler here is representing a vertical line. Are we together? Please take note of that. The ruler here is representing a vertical line. So the line of my graph and the ruler should touch themselves, that is, they should intersect at a single point only. Single point only. So it means that if I'm moving my ruler from left to right, the point in which the ruler and the graph, that's the straight line now, and the graph should intersect should be a single point only. So if you look at, if my ruler is at this point, where would they intersect? A single point. If my ruler is here, where would they intersect? A single point. If my ruler is here, where would they intersect? A single point only. So looking at this particular linear function, it satisfies the condition, meaning that this is a linear, this linear function, this particular relation here is a function, because my vertical line intersects my graph at a single point as we are moving it. Are we together? Now let's come to the quadratic graph. Now, if we use our vertical line, if I move my ruler from left to right or right to left, how many points will the ruler, which is my vertical line, and the graph intersect? Take note, the condition is that they should intersect at a single point only. If they don't intersect at a single point, then it's not a function. So what we do is, if I move my ruler, if my ruler is at this point here, that's this point, how many points will they intersect? Just a single point only. If my ruler is here, they intersect here. If my ruler is here, where x is equals to 0, they intersect at a single point, which is this point. If my ruler is here, they intersect here. If my ruler is here, where will they intersect? At this point. So, as my vertical line, which is represented by this ruler, moves from left to right, you notice that the graph and the line intersect at a single point only. Single point. So this also satisfies the condition. So that means this graph is a function. Now let's come here. If I move my ruler from left to right or right to left, how many points will the vertical line, which is the ruler and the graph, intersect? So this, if it is here, it intersects at a single point. If it is here, it intersects at a single point. If it is here, it intersects at a single point. If it moves here, it intersects at a single point. So this also satisfies the condition, meaning that this is a function. Now if we come here now, if my ruler is here, at this point here, it intersects at a single point. If my ruler is here, it intersects at a single point. If my ruler is here, it intersects at a single point. When it is here, single point. When it is here, also single point. So if you know, if I move my ruler from left to right or right to left, the vertical line and my lines of the graph will intersect at a single point. Now, coming here now, if I move my vertical line, which is represented by the ruler, from left to right or right to the left, will it intersect at a single point only? Now, at this point on the y-axis, if my vertical line is on the y-axis, it will intersect at a single point only. But if my vertical line moves here, how many points does it intersect? 2 points. If it moves here, how many points does it intersect? 2 points. If it moves here, how many points does it intersect? 2 points. So it means that this is not a function. This particular graph here is not a function. This is a function, this is a function, this is a function, this is a function. But this is not a function. Why? Because my vertical line intersects at 2 points with the graph. So this is not a function. So this is what you have to have at the back of your mind before we look at types of functions. Now, in types of function, we have majorly two types of function. We have the one-to-one function and the onto function. One-to-one, onto. So we have one-to-one, one-to-one. Another name for one-to-one is injective function. Injective. Then we also have what we call onto. Another name for onto is what? surjective. Surjective function. So these are the two types of functions we have. But if you combine the two of them together, we now have what we call bijective function. But before we get there, let's understand what is a one-to-one function and what is an onto function. One-to-one, onto. One-to-one function. A one-to-one function is actually, I think to understand it better is using, let's use mapping diagram to explain it better. So I want to draw two functions. This function has domain x and range y. I have a function x. Now I have elements here. Let's say I have -3, 0, 4, 5. Here I have 2, 8, -2, and -10. So I have this comes here, this goes here, this goes here, and this goes here. Now I also have another function. Let's say I have function P here and Q here. Let's say this function is G. I have elements x, y, z, and I have elements m and n. So I have this comes in, this comes in, and I have this one coming here as well. Now looking at this now, look at these two functions. First of all, the first question, are they functions? The answer is yes, they are all functions. Because if you look at, they satisfy the condition I gave for mapping diagram. So these two are functions. Now, but one of them is one-to-one, while the other one is not one-to-one. And which of them is that? Now, this function is one-to-one. Why is it one-to-one? It is one-to-one because for every element in your domain, it has one and only one image. And if you notice, they don't share their image. Two elements don't have the same image. Every element has its own unique image. So the image of -3 is -10. It has its own image. 0, the image of 0 is what? 8. It has its own image. The image of 4 is 2. The image of 5 is what? -2. So every element has its own unique image. So it's like looking at a family that the mother, let's say a man marries 10 wives. As the man married 10 wives, the man said, every wife must give me one child only. You cannot give more than one, just one child. One child only. So every child, all the wives have one child. So the first wife, one child, second wife, one child, third wife, one child. How many children will the man have? 10 children from 10 wives. So one per child, one per child. Such a relation is a one-to-one. That relation between the mother and the child is one-to-one. One-to-one. Are we together? If you look at that, that's one-to-one. So everybody, no two images here, no two elements here have the same image. So this is one-to-one, but this is not one-to-one. Why? Because two elements have the same image. So if you look at the image of x is n, the image of y is m, the image of z is also m. So since the two of them are sharing the same image, this is not one-to-one. Not one-to-one. But this one is one-to-one. This is one-to-one, this is not one-to-one. So coming back here, if you want to look at this, let me show you. If you look at graphically, a linear function is a one-to-one function. A linear function is one-to-one. But a quadratic function is not one-to-one. A quadratic function is not one-to-one. But a linear function is what? One-to-one. And that is very important to take into. A linear function is one-to-one, but a quadratic function is not one-to-one. So that's it. Okay, so this is one-to-one function. Now let's look at onto functions. Functions, we also use arrow diagram to explain onto functions so that you understand better. For onto function, let's say I have a function A, B, C, D. Here I have W, X, Y, Z. Okay, let's just say W, X, and Y. Then you have this, this, we are trying to get the function so that I can explain. I have 1, 2, 3, 4. Here I have -2, -3, -4, 0, 8. So let's say this comes in, this one comes in, this one comes in, and this one comes in. Now look at this particular function here. Looking at this function, you notice that two elements are mapped here. I mean, this function is not one-to-one, right? Good. But what do you notice about all the elements that are in your range? All the elements in your range are images of elements in your domain. If you have a function in which all the elements here, which we call the range, are images of elements in your domain. If you have such a function is called onto function or surjective function. A function in which all the elements in the range are images of elements in the domain. Then such a function is called injective and onto function or surjective function. Now, but if you look at this, is this a function? The answer is yes. Even though we have an element here that is not mapped or that is not an image, this element is not an image. But is this a function? Yes, it is a function. This is different from the other case. If you notice, if you still recall, when we were talking about, you can play back the video and look at it. When we were talking about functions using arrow diagram, if a relation is a function, I told you that if there is an element in your domain that is not assigned or mapped to any element in the range, then that is not a function. But here it is different. Here, all the elements here have been assigned. But there is an element here that is not assigned. So, this kind of function is not an only function. For a function to be an onto function, all the elements here must be assigned to the element here. All the elements here must be assigned to the element here. Now, in this kind of case, this set here, which is our set of output, is not called range again. If you still recall, when we started the video on functions, when we started functions, I told you about range and codomain. I told you there is a difference between them. Now, when you have a case like this, in which all the elements here are not assigned to the element here, then you don't call this Q again, you don't call it range. What you call it is what? Codomain. So this is your codomain, not the range. The range will be made up of only the elements that have been assigned. That is what the range will be made up of. So if you want to find your range here, your range will be, our range will be Writing using set notation, it will be -2, -3, -4, and 0. This is our range. But the entire set here is called what? Codomain. Because not all the elements here are assigned to here. So in a condition which not all the elements here are assigned here, then such a function is not an onto function. So this one is an onto function because all the elements here are assigned. Although this is not a one-to-one function because two elements here have the same image. Two elements have the same image, but it's an onto function because all the elements here are assigned. So for a function to be an onto function, all the elements here must be assigned. And if all the elements here are assigned, then this is called the range. So in such a case, we can say that if the range is the same as the codomain, if the range is equal to the codomain, then such a function is what? An onto function. So these are the two types of function we have. Two types of function. Now, what if you have a function that is one-to-one and onto at the same time? For example, you have a function x, y. This function is f. I have -3, 2, and 5. I have 0, 8, -10. So this comes here, this goes here, and this comes here. What do you call this kind of function? If you notice, this function is both one-to-one and onto. Why is it one-to-one? Each element here has its own image. Every element here has its own image. Right? So every element in your domain has its own image. And also, all the elements here in your output set are assigned. So this function is both one-to-one and onto. And if a function is one-to-one and onto, it is called bijective function. Bijective function. So we are going to stop the video for types of function here. Then in our next video, we are going to be looking at some special functions. And the special functions we'll be looking at constant function and composite functions. Then before, we will now look at inverse function. By the way, to find an inverse function, you can only find an inverse function of a bijective function. So for you to find the inverse of a function, that function must be one-to-one and onto. The function must be one-to-one and onto for you to be able to find its inverse. So thank you very much. Please, for anything you don't really understand, let's meet at the comment section. Just drop your comment and we'll talk about it.